Right, today we'll study fluid mechanics. Okay, so we'll apply all the laws we've studied to fluids. And when we say fluids, it's liquids and gases. Okay? All right, so you've studied the three states of matter. Here's a gas, here's a liquid, and here's a solid. Okay? So in solids, the atoms are in fixed locations. So if you have this atom here, you can come back 3 years later and the atom will still be there. Okay? In a liquid and gas, of course, the atoms are moving, molecules are moving about randomly. Okay? And you see this guy here now, a second later he won't be there. Okay? You don't know where he'll be. Okay? So the difference between liquids and gases is the density. Okay? You'll see that in a second. Liquids are about 10 times, 100 times denser than gases. Okay? Solids are 1,000 times, 10,000 times denser than gases. Okay. Okay. So we'll come to the densities in a second. Okay. So we'll study two subjects in this chapter. Fluid statics will study properties of liquids when they're at rest. And fluid dynamics will study properties of moving fluids. Okay? What we'll study is laminar flow. So when fluids are moving in a nice orderly fashion like that. Okay? All right, so here's density. Density is denoted by rho. It's the mass per unit volume. Okay. And so let's see, density for air is 1 kg per meter cube, 1.3 kg per meter cube. Here's a meter cube. This guy is a meter cube. This much air will weigh about 3 pounds. Okay. So there's the density of air. Here's the density of water. The density of water is about 1,000 times greater. So what that means is the density, the volume is 1,000 for a given mass. The volume is 1,000 factor less. Okay. So what that means is if gas molecules are this far apart, in liquid the molecules are 10 times closer. Okay. So the density of liquids is 1,000 times greater. And the density of solids, for lead for instance, is about 10 times greater than that of liquids. Okay. So if in a gas the molecules are 20 centimeters apart, in a liquid they'll be 2 centimeters apart. In a solid, they'll be 1 centimeter apart. So that's what that density means. Okay. All right. Kinsha, come on. So Violet got perfect score to here. I thought I saw you earlier. Congratulations. All right. So one of the things fluids can do is exert pressure. Okay, so you immerse an object like that in a fluid and you'll see that the fluid exerts a pressure. The fluid exerts a force which is perpendicular to the face, and pressure is defined as force per unit area. Okay. The units are, of course, newtons for force, meter square for area. So Newton meter square. And this is given the name Pascal after Mr. Pascal, who did work in this area. All right, so if you're here, the pressure is atmospheric pressure. And what you find is if you go inside a liquid, at this level, the pressure is atmospheric pressure, and that's denoted by P0. And as you go deeper into a fluid, the pressure increases. The pressure increases by this much. Rho is the density of the fluid. G is the acceleration due to gravity. And H is the height to which, or the depth to which you've gone in the liquid. Okay? And it turns out, so, well, the density of water is 1,000 kg per meter cube. 1,000 times G is 10, that's 10,000. And if you go to a depth of 10 meters, the pressure will be 2 atmospheres. Okay? So if you go to a depth of 33 feet, the pressure now underneath there is 2 atmospheres. If you go to 66 feet, what will be the pressure? So every 33 feet, the pressure increases by 1 atmosphere. So if you go to 66 feet or 20 meters, the pressure will be 3 atmospheres. Okay. All right, so that's what this formula is telling you. The pressure inside a liquid increases. Okay, this is the atmospheric pressure, and that's how much the pressure increases by. Okay. All right, so here's a manifestation of that. Because the pressure increases as you go deeper, the force exerted by this fluid is pressure times area. So for a given area, as the pressure is increasing, the force is increasing. And that's why dams you have to make, as you go deeper and deeper, the walls have to be thicker and thicker. You know? All right, here's another illustration of pressure. Okay. So at a spout, the pressure is atmospheric pressure because the spout is exposed to the atmosphere. Okay. And if the pressure difference driving this water is this pressure, the pressure of this column, that is the pressure right there, minus the atmospheric pressure. Okay. So greater the pressure difference, greater the velocity with which the water will come up. Yeah. So here the pressure is high, the pressure difference is higher, and so the water spout is coming out faster. Okay. Now, if you had a device like this, if you put honey and an identical device, and if you put water, which will come out faster?
The water will come out faster.
The water will come out faster. Okay. So honey has more viscosity, friction, and so you need a greater pressure difference to get the same flow rate. But here's an interesting fact. For 0 viscosity, okay, if you drop an object this height, you can calculate the speed at which it will be going. That's the exact speed at which this fluid will come up for 0 viscosity. Okay? All right. Okay, so the pressure at this depth in the fluid was given by that. That is atmospheric pressure plus the pressure due to this column of liquid. Okay, now we define something called gauge pressure because most gauges that you buy in the store to measure pressure, they don't actually measure the actual pressure. What they do is they measure the actual pressure minus atmospheric pressure. Okay, so this is called a gauge pressure. Okay. So the pressure that instruments measure is actual pressure minus gauge pressure. So in your car tires, so by the way, 1 atmospheric pressure is 1 atmosphere in PSI is about 15 PSI. Okay. And your car tires, the pressure is 30 PSI, but that's a gauge pressure. So the actual pressure in your car tires is 45 PSI. Okay. So atmospheric pressure, which we've been calling P0, is actually 100,000 pascals. In SI units, it's 10 to the power 5 pascals. Yeah. All right, so this is, and remember pascals is 10 to the power 5 Newton meter square. And newtons is, so newtons has the units of weight, so you can think of this as mg. G is 10, so that's 10 to the power 4 kg times g per meter squared. Okay, so atmospheric pressure, you can think of the atmospheric pressure as you take a 1 meter column of air. Okay, so 1 meter column, square column is about the size of this table. And this air going all the way to space, the weight of that column of air, the mass of that column of air is 10 to the power 4 kgs. And that's the mass of roughly a school bus. Okay, so this much air all the way to space weighs about a school bus. Okay, so that's what you can think of. All right, so roughly, if you look at your chest, your body, you got a school bus sitting on you. So why aren't you collapsing?
Surface area?
Hmm?
Surface area it's spread out on?
So inside your lungs, the air is at that pressure. So it's pushing you with an equal force from the inside. So what happens if you go diving? Let's say you're diving 33 feet. Now the pressure is 2 atmospheres.
The internal pressure is still 1 atmosphere?
So you have to breathe air at 2 atmospheres. What do you, when you dive to 66 feet? I'm sorry? There you go, my friend. Okay. And see, in that soda, what do you have? You have gases mixed in that liquid. The higher the pressure, the more gas will mix in that liquid. So you go deep diving, and then if you come up too fast, all that gas mixed up will bubble out. It'll bubble out in your joints, and that hurts like hell. What's that?
And then you might die if you go up too fast.
Okay, so you haven't died, but you have experienced the pain. Have you?
No.
No? Oh, but you know about it. Okay. All right, so 1 atmosphere is, so you can think of that, so that's one way of thinking about it, okay? So similarly, we said if you go 10 meters deep, that also weighs 10 to the power 4 kg. That column of water will also weigh 10 to the power 4 kg. All right, so here is a instrument that measures atmospheric pressure. It's called a barometer. Okay, and so if you make a barometer with mercury, so you can think of this as like so. So here's a mercury thing. Here's a mercury barometer. And this column is 76 centimeters. And this is perfect vacuum. Okay. And what a barometer is doing is, like a scale. Oops. When you have a scale, when two things are balanced, they're of equal weight. So this column of mercury is balancing an equal column of air, a column of air of equal width all the way to space. This is balancing that. So that's what the barometer is doing. Okay? So to make a barometer, what you do is you take a tube like that, fill it with mercury, hold your thumb to it, and then invert it into a vat of mercury, and you have yourself a barometer. Okay. What is this showing you?
Oh, regardless of the surface area exposed, it's going to feel the same pressure.
Regardless of the shape, okay? So the height of the mercury column is the same. Okay? All right, so what this is showing, what this picture is showing you is this is a slab of air. So this is this slab of air. Does this slab of air weigh anything?
Yes.
Okay, so why isn't it falling down?
It has air below it,
What's that?
because there's air below it.
Yeah, well, it's got air above it too.
There's denser air below it.
Very good. Okay, so since it's not falling down, okay, so this thing has a weight, like we decided. So there must be an upward force holding it up. Well, how do you get the upward force? Well, the pressure here is higher than here. Okay, so just from logical arguments, now you've figured out that the pressure decreases as you go higher up. Okay, and you guys have learned the ideal gas law. Pressure is N RT divided by V. So if the pressure decreases, we'll assume that the temperature is the same, and for a given volume, the number of moles of gas is decreasing. Okay, so the density of air is decreasing, as our friend just said. Okay? So that's what's happening. And if you follow through the arguments, I'm not going to go through the details. What you'll see is the pressure decreases exponentially. Okay. In fact, you climb up 5 miles. Okay, so space is defined at, when they were offering prizes to go up to space for private rocket companies, they would say you go up to 100 kilometers, about 60 miles up, and you reach space. But you start climbing and you climb 5 miles and you've crossed half the atmosphere, by weight. Okay, so the pressure decreases exponentially. And here, this is interesting, this expression, mgy, see that's the potential energy of a single molecule divided by kT. You'll learn about this in physics too. K is the Boltzmann's constant and T is the absolute temperature. Okay, so if you put these numbers in at about 9 kilometers, if you climb 9 kilometers, okay, the pressure and the atmospheric density decreases to about 35% its ground level value. So this is about the height of Mount Everest. So if you're on top of Mount Everest, the pressure is about 35% that of ground level pressure. Okay. That's the oxygen content you have, yep.
Is that one, like when you're going up a steep grade,
Mhm.
like it's harder to breathe?
Yep. Yep. All right. Yeah, you have to be in shape to do that kind of stuff. And that's why planes fly at 11 kilometer elevation. So there, the atmosphere is about 20% the ground level atmosphere. So you have to pressurize cabins. Otherwise, you won't be able to sell tickets to passengers. Yeah. All right, now we'll study Pascal's law. We use this phenomenon everywhere. Okay, so let's say you have an enclosed fluid. Okay, so this is oil, let's say, an enclosed incompressible fluid. And this is how all hydraulic systems work. Okay, so the pressure, what is the pressure here? 1 atmosphere. Okay, it's exposed. The pressure here is 1 atmosphere. What is the pressure here?
1 atmosphere plus the density times depth.
Very good. We'll call it 1.5 atmosphere. Okay, and there's 1 atmosphere there. Okay, now what we're going to do is we're going to put a piston on it and apply a force. Okay, so we will increase the pressure by that amount. Okay, and so we'll say, let's say, we increase the pressure from 1 atmosphere to 1.3 atmospheres. Okay, so at this location, we increase the pressure by 0.3 atmospheres. What Mr. Pascal realized is, if at a location for an enclosed fluid, if you increase the pressure by a certain amount, the pressure increases by the same amount everywhere. So what did this pressure go to? 1.8 atmosphere. The pressure increased by the same amount here. Okay, and so that's what this is saying. So you increase the pressure at this location by that much, the pressure increased by the same amount there. Okay, that's F2 by A2. So you push with this force, and this is the output force you got. Okay, so F2 was equal to A2 over A1 times F1. Let's say you make this area 100 times greater than this area. That's easy to do. If the input piston is this big and the output piston is that big, that area is 100 times greater. So for an input force of 100 pounds, you get an output force of 10,000 pounds. Yeah, so that's Pascal's principle.
Does the entire system have to be enclosed for this to work?
Yep.
Okay, so in your example, the other side is capped or?
Yeah, right, yeah. So this is all how your hydraulic systems work, your brakes, your clutches, and you know.
What would be an example of a compressible fluid?
Air.
Oh, good point.
This is how those dentist chairs work and all that kind of stuff.
Is that how way stations work?
I'm sorry?
Oh, what about way stations? Oh, no, that's.
No, that's got to be a spring. Yeah, that's a spring. Okay. I was going to. Okay. So this is what is this guy?
A lift?
A simple machine. What does a machine do? It's a force multiplier. Okay. So this gave you a multiplication of a force. Is this free lunch? So what's the price you're paying?
Distance?
Very
force
good,
supply?
very good. Okay. So no free lunches. Input work is equal to output work. Okay. So if the input force is 100 times less than the output force, then the output distance is 100 times less than the input. Okay. So work in equal to work out. So input force times input distance is equal to output force times output distance. Okay. When is that true? When is this true? When there's no friction, it's never true. Okay. In real life, I mean, so you always get less. Yeah, but you were right. Okay. All right, so the price you're paying is the output distance is the inverse of the input distance. Okay, so.
Okay, I found this on the web for the price of the output. Check it out.
Siri is a little too enthusiastic today. All right. All right, the next phenomenon we'll talk about is buoyant forces. Okay, you saw that as you go deeper into a liquid, the pressure increases. Force is pressure times area. Okay, so let's say you have an object like this. The pressure here is higher than the pressure here. So if you immerse an object in a fluid, it will feel an upward force. Okay. So for instance, you can do the following experiment. You can go stand on a scale, and gravity pulls you down, and this scale is pushing you up with an equal force, and that's the weight you read. Okay. Now, if you do the same thing underwater, okay, because you're underwater, the water is pushing you up. Gravity is still the same, and so this spring doesn't have to push you up as hard. So if you weigh yourself underwater, you actually weigh less. In fact, you're weightless underwater. because the buoyant force will equal gravity for humans, okay, essentially. All right. Anyway, let's come back to this. So the pressure below is higher than the pressure above, and so there's a net upward force on this object, and that's called the buoyant force. Okay? And Mr. Archimedes told us precisely how large this force is. Any guesses on how large that force is?
Density of water?
I'm sorry?
The density of water?
It's related to the density of water if you're immersed in water. What Mr. Archimedes realized was this upward force is equal to, you displace that much water, it's equal to the weight of the displaced water, or the weight of the displaced fluid. Okay? All right, so Mr. Archimedes said the buoyant force is equal to the weight of the fluid displaced by the object. Okay? And so if it's, so the buoyant force is the density of the fluid times the volume displaced times gravity. Yeah. So inside a fluid, the apparent weight is the actual weight minus the buoyant force. And our density essentially is the density of water, so underwater you are essentially weightless. Okay? And that's why NASA, when they train astronauts for weightlessness, they do it in pools underwater. Okay? All right, this guy is floating. So what does that mean? Okay. The weight of this object is being balanced by the buoyant force. Okay? So the weight of this object is being balanced by the buoyant force. Okay, well, we just learned that the buoyant force is equal to the weight of that much liquid. Okay? So when an object floats, the density of the object is less than or equal to the density of the fluid. Okay. That's only when how you can float. Okay. And so if the object's density is 60% the density of the fluid, okay, 60% of the object is underwater. If the object's density is 80%, 80% of the density is 80% of the object is underwater. Okay, for ice, the density of ice is 90% that of water. So 90% of an iceberg is underwater. Okay? Every captain knows that. Okay. So if you can see this, well, you don't know what the iceberg is underwater. It could be like that. You don't want to come close to an iceberg. And this guy captaining the most expensive ship runs into one, right? This was a few years ago. All right, so that was fluid statics. So we studied properties of fluids at rest. We mentioned density. We studied pressure as a function of depth. We studied Pascal's law. We studied Archimedes' principle. Okay. And what else did we study? Yeah, that's it. Okay. All right, now we'll graduate to moving fluids, okay, fluid dynamics. Yeah. So, Okay. So here is a cube of ice. What if I put this, press down on this cube of ice and put it under water and let go? What will happen?
Back up,
I'm sorry?
it'll float back up.
Why does it float back up?
Because the buoyant force exceeds the density of water.
Very good. Okay. The buoyant force is equal to the weight of this much displaced fluid, and that is greater than the weight of the ice cube. So the buoyant force is greater than the mg, and so it rises up. Okay. So there's a buoyant force that's forcing it up. Okay. So let's do the following. We'll take a packet of air. We'll heat it. What happens to it?
It rises.
It expands, its density becomes less than the density of the surrounding air, and so it'll rise up. Right? How long will it rise up? How long will it feel a buoyant force?
Until it reaches the same density air in the atmosphere.
Very good. So as long as it's warmer than the surrounding air, it'll keep feeling a buoyant force, and it'll keep rising up. Okay? And since the force is there's a net upward force, it keeps accelerating. Okay? All right. So let's look at this. Okay, what is this guy? What do you think this is? Smoke rising from a cigarette. Yeah? All right. So that's burning cigarette tip was warming the air packet, and that air packet is rising. And since it's accelerating, it's going faster and faster. And what is happening?
It's spreading out.
So you see, this is laminar flow. What we mean by laminar flow is if two particles were neighbors, they'll stay neighbors. But here, the flow has become turbulent. So it seems like once you pass a critical speed, the flow becomes turbulent. Okay? Now, this part is hard to describe. So when we talk about fluid dynamics, we will only talk about this portion. Okay? When the fluid has nice laminar flow. Okay, so here's a joke. Say, Werner Heisenberg, he's a famous physicist, once said, given the opportunity, when I meet God, I'm going to ask him two questions: why relativity and why turbulence? Yeah, I really believe he'll have an answer for the first. So he's saying nobody understands turbulence. Okay? So we won't talk about it. Okay, so here is laminar flow. Here is turbulent flow. Okay. The reason we talk about this is you will be interested in flow rates. Yeah. And so if you want to make fluid flow through a pipe, okay, you have to maintain a pressure difference. That you have to maintain a pressure difference if there is viscosity to the fluid. That is, a non-viscous fluid as it doesn't have any friction. So the flow rate is pressure difference divided by the resistance, okay, to flow. Resistance depends on viscosity and all that. We'll come to that later. But if the flow becomes turbulent, resistance increases. And if you wanted to maintain the same flow rate, you would have to increase the pressure difference. So for instance, your heart is pumping and maintaining a flow rate of a blood through your body. Okay. So if your flow becomes turbulent, then your heart would have to work harder to maintain that flow rate. Okay. Okay, so this graph tells you this is the perfusion pressure, that is the pressure difference you maintain between two ends of a pipe. And this is the flow rate. Okay, if the flow becomes turbulent, so this is plaque in your arteries and stuff like that, and if the flow becomes turbulent, see, for a given pressure, Okay, when the flow is turbulent, the flow rate decreases. If the flow is laminar, for the same pressure, you have a higher flow rate. Okay. Okay, so turbulence is not good most of the time. Okay. So again, this is laminar flow, turbulent flow. Viscosity is friction in a fluid. Okay, you guys all understand that honey is more viscous than water. So if you wanted to pump honey down a pipe, or pump honey or water down a pipe at the same gallon rate a second, which one will cost you more?
Honey.
Pumping honey will cost you more. Okay? You have to maintain a high pressure difference. Okay? So viscosity characterizes the degree of internal friction in a fluid. Yeah. Viscosity causes parts of kinetic energy of a fluid to be converted to internal energy. You push the fluid and it acquires a velocity, but that because of friction, some of that velocity gets converted to heat. The liquid slows down and then you have to push it again. Okay? All right. So we'll consider an ideal fluid flow. It's the viscosity is the fluid is non-viscous. So what we're saying is, when you push, get the fluid moving, and it won't stop. It will keep flowing. Yes. But all real fluids are viscous. Okay. Flow is steady. What we mean by that is, so here's a river flowing, and if here's the velocity of the river now, you can come back 5 minutes later, and that will still be the velocity of the. So that's flow is steady. Fluid is incompressible. That is, you can't compress a fluid, but we'll still apply these laws to air and stuff like that. Okay, even the air is compressible. We'll consider air in situations where it's not being compressed terribly much. Yeah. And the flow is irrotational. Okay, so we'll consider fluid flow like this and not like this. This is, so if you put a paddle, the paddle will start spinning here. Okay, so this is rotational flow. Okay. If you put a paddle here, it won't rotate. This is irrotational flow. Okay. So, okay, we are going to give you a few laws for fluid flow under those conditions. We're considering the fluid to be ideal and the flow to be laminar. Okay, non-turbulent. Okay. Well, this will apply whether it's laminar or not. But this is equation of continuity. What this says is, if 10 gallons a minute are flowing in, and if this pipe has no holes, how many gallons are flowing out a minute?
10 gallons.
10 gallons, as long as it's incompressible. Okay. So, if the area of cross-section of the pipe changes, this is the flow rate. Area of cross-section times the velocity of the flow equal to A2 times V2. Okay. So if the area doubles, the speed decreases by a factor of a half. Okay. The area, if you have the area, the velocity increases by a factor of 2. Okay. Did you guys know this law?
It's Venturi.
Yeah. Everybody knew this because when you water using a hose and you want the water to go further up, what do? You decrease the area. So you intuitively knew this law. That's what you were doing. Yeah. All right, so when I throw this keychain up, what happens to the speed?
Decreases when it's going up and increases when it's going down.
Yeah. Why did it decrease as it was going up?
Force of gravity being applied to it.
Mm-hmm. Another way of saying it is, kinetic energy was being converted to potential energy. Okay. So similarly, if a liquid flows up, its potential energy is changing. Okay. So Mr. Bernoulli investigated all this phenomenon, and what he found was the sum of these quantities remains constant. The pressure at a given location, okay, and this is for ideal fluids, so this won't apply for honey. Okay. We'll apply it to water. We'll say its viscosity is small. Okay. So again, this is for ideal fluids. The combination of pressure, this is the kinetic energy per unit volume, and this is the potential energy per unit volume. Okay. So the sum of these three quantities will remain constant. And this is Bernoulli's equation. Okay. So the flow has to be non-turbulent, irrotational for equation to be valid, and non-viscous. Okay. So it turns out this is a result of the conservation of energy principles. Okay. So again, the sum of these three terms has to be constant. Okay, so pay attention to this. This is very important. I want you to remember this for the rest of your lives. Okay. Okay, so here's a pipe, and so it's at the same level. The y is not changing. So we just learned that this is 0.1, we'll call this 0.2, okay? So the sum of these three quantities should be constant. Okay? What happens to the speed of the fluid when it comes here?
Accelerates.
It increases because the cross section is lower, okay? So P1 plus 1/2 rho V1 square plus rho GY1 equal to P2 plus 1/2 rho V2 square plus rho GY2. Okay, the heights are the same, so this term cancels. Okay, you just saw that at point 2 the velocity is greater. This is higher than that, so this has to be lower than this. Okay, so what I want you to remember is when a fluid speeds up, the pressure at that location drops. Okay, so Mr. Bernoulli will tell you that. Right? Everybody understand that? Okay, that's how you make planes fly. All right, so here's a plane. Why is it not falling? Here's the weight of the plane. Why is it not falling off the sky? There must be a force, a lift that is keeping up there. Okay, here's how lift arises. So this plane is flying in this direction, and air is flowing like that. Because of the shape of the airfoil, this air has to travel a greater distance. It has to travel faster. When air is traveling, fluid is traveling faster, the pressure is lower. This pressure is lower, this pressure is higher, and that's what provides the lift. Did you finish? Okay. Okay, so faster a fluid is flowing, the lower the pressure. Okay. I don't know if you guys have experienced this on the highway. So here's all this air, and you're driving by next to a truck, and all this air has to go through a narrower area. It's going faster, the pressure is lower, and you feel a attractive force towards the semi. Okay. You might also feel this. You have a semi, and they'll have dust in there, sand or whatever, and they have a cloth on top preventing the debris from flying out, but you still get particles coming through. Why is that?
Tarp is moving.
I'm sorry?
Tarp is moving, it lifts up.
Okay, so the air above the tarpaulin is flowing, the pressure is lower. This air was still, the pressure is higher, again, it was flapping on the tarpon. All right. All right, so this is what I want you to remember the rest of your lives. If you have a faster moving fluid, the pressure at that location decreases. And so that's how this device works, okay? What do? You blow air across this pipe. The pressure here decreases. The pressure here decreases. Atmospheric pressure pushes this liquid up there, and this gets caught up in this flow, and you spray that liquid, okay? So I guess the technical term is embedding. Okay, so you're embedding this fluid in that flow. Yeah. Okay, so I'll tell you about this effect. Anybody play tennis?
Many a year ago.
A few moons ago, okay. Anyway, did you do topspin?
Don't
No.
remember, I said many, many years.
Okay. Anyway, so here's why you do topspin. You hit the ball with the topspin, it gives you more room for error. Okay. So anyway, this ball is traveling in this direction, and when you put a topspin, the ball is spinning like that. And the ball is going like this. And so the airflow is such that this air and the fuzz also grabs the air, so it's flowing like that. You see, this air has to travel a greater distance than this air. This air is traveling much faster than this air. Faster travel, the pressure decreases here. And so there's a net downward force on it. So the more topspin you give and the harder you hit, it's going to fall inside the line. Okay?
So if you make it rotate sideways, would it have a...
Right, sideways, yeah. All right, so I'll show you guys a fun video. Okay. You guys have seen this video? What's that?
And what we're going to do is demonstrate from the very top
Well, you
the
gotta
effect
see
of
it.
spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens. All right, you guys good down the bottom?
Sit down here, thank you, we're watching.
Ready?
So no spin, no sideways force, okay? Essentially.
How's the curves? Well, yeah. Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, that the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it's falling, so that was really cool. Alright, ready? Whoa, look at that go! It's incredible.
So you want those to get back in the water, do you?
Never gets boring, no matter how many times. All right. So that's the Magnus effect. Okay, again, what is it? Faster the fluid is flowing, the lower the pressure. Okay? All right, now we'll talk about viscosity. What is viscosity?
Internal friction of fluid,
Yep. And what does friction do?
slow it down.
Converts kinetic energy to heat. Okay? All right, so here's how you measure viscosity for a fluid. So here's a movable plate, and what you do is you have to figure out what force do you have to apply to maintain a constant speed on this plate. Okay, if you apply a force, it should accelerate, but why is it going at constant speed? Because there's friction in the fluid. Okay, if there was no friction in the fluid, then it would accelerate. Okay, so the force you have to apply to maintain this constant speed, that's the that's the viscosity of the fluid. A is the area of cross-section of the plate, area of the plate, and L is the distance between the top plate and the bottom plate. Okay. Okay, that's the viscosity. And of course, this number for honey would be greater than for than for than for water. All right. So in automotive oils, do you want high viscosity or low viscosity? Hello there, Aaron? So when you guys do engine oil, do you like high viscosity or low viscosity?
I mean, it depends on the application.
Okay, so in Florida, it's low viscosity.
You can go higher.
Okay.
Typically when it's colder, you want it a little bit.
Less. Okay. Yeah. Yep. All right. So if you have viscosity, you want to make a liquid flow. This is the flow rate. You have to measure, maintain a pressure difference. So higher the viscosity, higher the pressure difference you have to have for the same flow rate. All right. So in Alaska, where they pump oil, you might have heard of this. They put heating coils around the pipes. They heat the oil. Why is that?
Help it maintain a lower viscosity.
So you lower the viscosity, so then you have to maintain less of a pressure difference to maintain a flow rate. So you're spending less money on heating the oil. The savings due to pumping is greater. Okay, so that's why you do that. All right, guys, that ends